Okay, any questions, please? Okay. Okay. So we could always do a little bit of review. So we go back to the beginning. We have the non-relativistic law of gravitation, that's Newton's inverse square law, gives the potential and force are related like this: potentials, forces, and tidal force. Sorry? Or I'm really sorry. Okay. So now it's okay? So we have the force law, Newtonian force law, the potential relating to the force, and the tidal force equation. Huh? What should be done? Oh, it's okay now? All right. So we want a relativistic generalization of this law, which is replace the Poisson equation by Einstein's field equations. And to get there, we start by recalling that the force in a gravitational field is independent of the mass of the particle. This is not true for any other force. This means that the motion in a uniform gravitational field is indistinguishable from motion in an accelerating frame of reference. And in accelerating, i.e., non-inertial frames, the laws of geometry are not that of Euclid, they are non-Euclidean. Hence, gravitation is the same as curvature of space-time, and the potentials are described by the metric tensor, which transforms like a second rank tensor. There are 10 potentials, and the equation of motion is found by extremizing this path length by integrating from the starting point A to the end point B. When you extremize this path length, you find this equation of motion, the geodesic equation of motion, which replaces Newton's law, second law of motion. So F equals minus grad phi equals ma is replaced by this, where the gammas are critical symbols. They are symmetric. They are the symmetric part of the connection, and antisymmetric part is known as torsion. Torsion is zero in general. Okay, the Newtonian limit of the geodesic equation is obtained by having only one non-zero potential, G00, related to the Newtonian potential phi by this relation. Substitute this in the geodesic equation of motion, and you get Newton's second law of motion in a gravitational field. The geodesic equation can also be written as the vanishing of the covariant derivative of the tangent vector of the geodesic, and the curvature is described by the Riemann tensor, which is a fourth rank tensor which has 20 independent components for this space-time related to critical symbols by this relation, and has these various properties. And you could construct the second rank Ricci tensor and the scalar curvature, which appeared in the Einstein equations. And this is how I introduced the current tensor, the current four vector, the energy momentum tensor, which is symmetric in the two indices, which describe the current of the momentum four vector. And under these conditions, this is the left hand side of Einstein equation. You put that equal to the energy momentum tensor on the right hand side. These are Einstein's field equations. And if there is a non-zero cosmological constant, lambda, they are modified to this. The Newtonian non-relativistic limit of Einstein equations is recovered as desired. This equation, Einstein's equations explain the precession of Mercury's perihelion, bending of starlight by sun, black hole solution we saw, gravitational waves we saw, cosmological solution we saw. And linearized gravity, where the metric departs just a little bit from the flat space-time metric. H mu nu is much less than 1. And if you define H bar like this, where H is the contraction of H mu nu, then the Einstein field equations become linear equations, which are analogous to the Maxwell's equations for the vector potential. If the source is zero, it is described gravitational wave. If the source is non-zero, describe a nearly Newtonian gravitational field, and from this metric we can compute bending of light as well as the gravitational redshift, both of which have been verified experimentally. Then yesterday we did the black hole solution. This is the Schwarzschild solution given by this metric, and we argued that if the radius of a spherical body is less than the Schwarzschild radius 2 gm by c square, then this object will necessarily be a black hole. And this is how you find orbits in the Schwarzschild geometry. This is the effective potential, which generalizes the Newtonian gravitational potential. And by solving this, you can find the trajectory. Okay, and this is how you find the precession of Mercury's perihelion, and then we discussed in quite some detail why this metric, the Schwarzschild metric, describes a black hole if the radius of the body is less than the Schwarzschild radius. Okay, so today now to the last topic. Okay, if you have any questions or doubts, please stop me. Okay, good. So now, what are we interested in? This Einstein tried right away after finding the Einstein field equations, but how to describe the universe. So it depends on what the universe looks like when Einstein was alive. The picture of the universe in 1915 was very different from what it is today. Expansion of the universe had not been discovered. That was discovered by Hubble in 1929. Neither was it clear that there are actually galaxies outside our own. What the universe looked like to astronomers is more or less the same as what you see today if you go to a village. The sky is good, dark nights, you look up, you see a lot of stars. And it was known that these lie on a disk, that the stars form a disk, which is called the Milky Way, a flat disk. That was known. But it was thought that that is the universe. It's so different from today. There were these so-called fuzzy nebulae, but what was not clear is whether they are within our galaxy or whether they are independent galaxies outside our own, so-called island universes. Distances were very hard to measure. So the picture was that our galaxy, the whole universe, and it is static. The stars are going around the center of the galaxy, but nothing is happening to the galaxy. The universe is static. So Einstein set out to find a solution to his equations. I'm sure you know the story. So he made these simplifying assumptions, which we all do even today, that the universe is homogeneous, namely same at every point, and it is isotropic, same in all directions. The homogeneous does not imply isotropic. Like on the surface of a cylinder, the distribution of matter can be homogeneous, but it is not isotropic. One direction is closed, the other is infinite. Homogeneity does not imply isotropy about every point, but isotropy around every point implies homogeneity. This we can verify very easily. Homogeneous, that is all over the place, it is isotropic. At every point it is isotropic, same in all directions. Then it will also be homogeneous. Okay. So Einstein, so is the universe actually like that? You know, a lot of research has gone in. Maybe when it is homogeneous, so maybe it is not. There's a debate even today, although the ones who are saying it is not homogeneous and isotropic are in a minority. But to be honest, there is a debate. But we make a simplifying assumption because it helps us solve Einstein equations. So this is known as the cosmological principle that the universe is homogeneous and isotropic. There was also something known as the perfect cosmological principle, homogeneous and isotropic, and doesn't even change with time, eternally the same. That's the perfect cosmological principle. That we are confident today is not true because the cosmic microwave background we talk about it's not possible to produce it using stars. It seems to be a leftover from a hot Big Bang, early beginning of the universe. So looks like the universe had a beginning, in which case the perfect cosmological principle is not viable, but the cosmological principle is still viable. Okay, let's wait here. So what did Einstein do? Einstein did not know about the universe expanding. So we will come back to this point three, but this one is okay. The Robertson-Walker metric describes a homogeneous and isotropic solution of Einstein equation. It's given that. What does this mean? At any given time, the spatial curvature will be same everywhere. So homogeneous, it has to be described by curvature. The curvature should be same everywhere. This curvature of the spatial section, not of space-time, can be either positive, zero, or negative. Zero is like flat space. So if you have a plane, take a three-dimensional version of a three-plane, which has three independent directions, dx, dy, dz. And if it is zero curvature, that is the case here, k equals zero. Or it can have a positive curvature, it will be a three-sphere, not two-sphere. Two-sphere is the surface of a ball, but the universe has three dimensions. It can have three closed dimensions and be what is called a three-sphere. So if k is plus 1, this is the spatial metric of a three-sphere. If k is minus 1, then this is the spatial metric of it's a, probably called a three-hyperboloid. Is that what the name? Open geometry. Open geometry, yes, yes. So usually the example of a negative curvature is hard to visualize, like the saddle of a horse, that it's a negative curvature, and this is the three-dimensional generalization. This is the spatial section. This spatial section, dr square over 1 minus kr square plus r square d omega square. Okay? K equals plus 1 is a three-sphere. It's a closed universe. You go in one direction, you come back, like on a sphere. K is 0 or minus 1 is infinite in extent. 0 means zero curvature, minus 1 means negative. So what can this three-dimensional surface do? It can expand the size, the scale can change with time. So the example is like you have the surface of a balloon. You inflate it by pumping air in it. Take any 2 points on the surface of the balloon, they start moving apart. They will still remain homogeneous. The point distribution will remain homogeneous. It would start homogeneous, but they'll start moving apart. That is measured by the scale factor. Scale factor measures whether the universe is expanding or contracting. So if A of t is increasing with time, it is expanding. If it is decreasing with time, it's contracting. So these are also what are called co-moving coordinates, r, theta, phi, meaning even though the balloon is expanding, if you choose a point, it has coordinates r theta phi. It will always have coordinates r theta phi, same coordinate. But the distance between 2 points will increase in proportion to a of t, the scale factor. But it's like wherever I go, my name will keep the same. That's my co-moving coordinate. Doesn't matter where you're. Same for all of you. That is what a co-moving coordinate is. It's an identifier which you carry for you all over. But that doesn't mean you cannot move around. You can move around. You can carry your name and go places. Same happens here. But there is a stretching which is possible. And this is the so-called cosmological time, and this is the Robertson-Walker metric, which, as usual, we will substitute in Einstein field equations and find the equations of motion for the scale factor. Okay, any questions?
Is there any evidence to argue that there was not
Okay, it's like this. This is my understanding. If you want to say what is the size of the observed universe? It's about 3000 megaparsecs, or 10 billion light years. 10 billion. The age of the universe is about 10 billion years. The distance that light could have traveled in that much as 10 billion light years, or if you want better units, 10 to the power 17 centimeters. You can compare, how much 10 to the power 7, lots of zeros. The galaxy size is like 100,000 light years. Milky Way, one end to the 100,000 light years. Andromeda is 2 million light years. And we can, and horizon, the observable universe, is 10 billion light. Now, I want to know what are the largest structures possible. Suppose there is a structure, large-scale structure which of the order of the size of the universe, 3000 megaparsecs. It's clearly not homogeneous. Homogeneity means, well, clearly it's not homogeneous. That's obvious. There are stars. Stars are not distributed homogeneous. They are in a disk. So you have to take a large enough cell, uh, big enough cubic cells here, and find out the mass density average in that. Take another cell, say 100 megaparsec inside, and see if you, after this smoothing, at least do you get homogeneous. You get what I'm saying? Now, so my understanding is that you make larger and larger telescopes to find larger and larger structures. This seems to be a non-ending process. So there is a debate. Many people tell you the largest structure we see may be of the order of 100 megaparsec, and that is the scale of homogeneity, 200 megaparsec. But some people are saying that no, there are larger structures, these superclusters. This is an ongoing investment. So, but life is much simpler if it is homogeneous. You can do cosmology. If it's not homogeneous, it's going to be a big problem. And the cosmic microwave background definitely isotropic. CMD you have heard of. That is isotropic. And then the question comes, if it is not isotropic around everybody, then our location is very special. Why, who are we? Why is it isotropic around us and not someone else? So it's a somewhat confused situation. The isotropy of the microwave background would suggest homogeneity because it would be likely to be an isotropic around anybody. But then what are these large structures doing, which are you're finding ever larger and larger structures? And yeah, we'll talk more. So right now, I'm happy to at least say it's an assumption because it yields results which agree with other observations. I'll tell you. So you cannot throw out homogeneity so easily because the model that we will make agrees with other. like nucleosynthesis data. Yeah. So what Einstein did, he plugged this metric in Einstein equations, and he was shocked that the solution was an expanding universe, right? And the universe is not expanding. Einstein's scared, equations are wrong. We are. So he modifies the equations by adding a cosmological constant, and by a suitable choice of the cosmological constant, he could get a static solution. So very happy. So he published that, and within a few years of that, Hubble showed that the universe is expanding, and Einstein realized that I could have predicted. You know, this is a famous story. Einstein realized that he could have predicted the expansion of it. So it is said that he called the cosmological constant the greatest blunder of his life. Why did he do that? Why he could have said the universe is expanding, you go and look for it. So then he again put the cosmological constant to zero. But today it has again come back. So if you read the history of cosmological constant lambda, which is followed the last 100 years, it keeps coming and going. If you ask me, I think it is zero. And there's a different reason for cosmic acceleration. But again, but the so-called standard model of cosmology assumes that the cosmological constant is non-zero, and that gives a good weight to this data. Oh, so that is the Einstein story. 1929, Hubble firstly showed that these so-called island universes or nebulae are outside our galaxy. They are independent galaxies in their own right. Not just that, they seem to be going away from each other. And so then, after that, Friedman and Lemaitre, along with Robertson Walker, found solutions to Einstein equations which describe an expanding universe, which is what we'll see just now. We assume that every galaxy is just one point, and the universe is a uniform fluid, a homogeneous and isotropic perfect fluid, no viscosities. It is a mixture of matter and radiation. Radiation came later. So matter and that matter is, if it is non-relativistic, it is described by only the energy density. So it's called, for example, dust fluid. Non-relativistic means the rate at the speed at which galaxies are going away from each other. If that speed is much less than the speed of light, then that's a non-relativistic expansion. And then you can neglect the pressures. If you neglect the pressure, such a fluid is called dust. So that's the name in cosmology. Dust is a fluid for which the pressure is negligible. Radiation is not dust. Electromagnetic radiation has a non-zero radiation pressure. P equals 1/3 rho by c squared. So rho is, or just c equals 1, P is 1/3 rho. That is the equation of state for radiation. P is 1/3 rho. The equation of state for a cosmological constant is P equals minus rho. Okay? So that's negative pressure. That's very special. That's very unusual. Normal matter and radiation have positive pressure. So that's understandable. If the pressure is ignorable, it is dust. If the pressure is non-zero, then if pressure is of the order of density, then it's a relative fluid, and radiation is P equals 1/3. Okay, so now let us substitute this metric in Einstein equations. This is what we get. We get two equations, very famous equations known as Friedman equations. One is a first order equation. So everything in this equation I have introduced already. Yeah? Lambda is the cosmological constant. So this is the first order equation. This is an example of a constraint equation. You see, It doesn't involve the second derivative scale factor. So the Einstein equations in this case, one of them is a constraint equation, and the other one is the equation of motion, second order equation for A double dot. And what is on the right hand side? Rho plus 3p plus lambda, and here only density. So for a moment, if you see if lambda is 0, just look at the case lambda is 0. And you have ordinary matter, rho plus 3p is positive, your rho is positive, p is positive, rho plus 3p is positive, there's a negative sign here, acceleration is negative. It is the same thing as you throw a stone up, it slows down and comes back. So, ordinary matter will, because of its gravitational pullback, will slow down the expansion. The expansion of the universe will be decelerating. If it is accelerating, as is observed first seen in 1999, then you have only one choice. Rho plus 3p is negative. But what to do? Rho plus 3p is positive ordinary matter. Bring in lambda. Lambda has p equals minus rho. That's the property of lambda. If you put p as minus rho, rho minus 3 rho is negative. And this becomes positive, the universe starts accelerating. So, if today's universe is dominated by the cosmological constant, it will accelerate. The rho plus 3p for lambda is negative, for ordinary matter and radiation positive, but this will dominate. In the early universe, so lambda is a constant. In the early universe, rho was higher, 3p was higher. In the early universe, this term dominates lambda. So the early universe was decelerating, it was not accelerating. If there was an inflationary phase, then there was an acceleration. Inflation ends, deceleration, and then for some reason it seems to be accelerating again, and there is a possibility that the accelerating phase in the early universe inflation is related fundamentally to the accelerating scale today. Whether inflation happens, we don't know. There's no direct evidence. It's a very popular theory, but it is not a part of standard Big Bang cosmology. Which the part that is confirmed with observation does not include, in my opinion, inflation. Okay, and here everything is positive. The left hand side is positive. The right hand side. So what will contribute here is the energy density part of lambda, and that is positive. So anything to ask about these equations? So one can solve them. These are not difficult to solve. Once you give P and rho, suppose rho is 0, pressure is 0, just dust, and you have only density, and suppose lambda is also 0. Then one can easily show that no, because the universe is expanding, the density will obviously fall as inverse of the volume. So the total mass is not changing. Mass cannot go anywhere. Density is falling 1 over the volume. It is falling as 1 over a cube. If it falls as 1 over a cube, you can easily then solve this equation, especially if k is 0. You will get a dot square going as 1 over a, so that will give you a going as 3 to the 2/3. Similarly, for positive k and negative k, you can solve this equation. For lambda equal to 0, the solutions are much easier. I'll show you the result of it. So there are three kind of solutions to this system. If suppose you also set p as 0, just have dust. Galaxies are like dust, so their motion is non-relativistic, at least if they are not far off. If k is positive, you have what's called a closed universe. Yeah, it goes to a maximum size and then recontract. And if k is 0, it will reach a maximum size at infinity. That's the bound marginal case open universe. And if k is negative, it will expand further. So that you can see from it. Suppose k is positive, bring it on the right hand side. And rho is positive, so it's A dot is positive, but on the right hand side you have a difference, rho minus K is positive. There will come a stage when rho will become so small that rho and the K term will cancel. You get 0, A dot will become 0, and then it will start recontracting. It's the same as the escape velocity of a rocket that so if you throw up a stone, it comes back. That's like a closed universe. If you send a rocket greater than the escape speed, it escapes, it goes away forever. That's like a open universe, and then there is a bounding case. Okay, so these are our fundamental equations. You can do things with them. And here are some very basic things we should know to work with these equations. Firstly, how do we know the universe is expanding? Very basic physics, I'm sure you know it. The light that is being emitted by stars in distant galaxies, its wavelength when received is higher than when emitted. This you can check. Suppose your hydrogen spectrum, hydrogen lines are emitted. What you are receiving is also hydrogen lines. So just from the relative position of the spectral lines, you will know that this is hydrogen. But every wavelength is shifted to a larger value. Why? That is what the expansion of the universe does, because uh, you can, if you want to make a simple picture, you can think of it as a gravitational redshift. It is being stretched by the expansion of the universe, and this is how you can quantify it. The redshift factor Z. Z tells you how much is the redshift. Lambda observed minus lambda emitted divided by lambda. This is the definition of redshift. And wavelengths stretch in proportion to the scale factor, the size of the universe. So this is also equal to the scale factor at the time when you receive the light minus the scale factor at the time of emission divided by the scale factor at the time of emission. And this is also equal to how far the star is, is the distance, the distance to the star or the galaxy, how far it is now, minus how far it was when it was light was emitted. Obviously, this is a positive quantity divided by the distance at the time of emission. This is how we quantify redshift. So, if lambda observed and lambda emitted are both equal, then redshift is 0, and then otherwise, redshift is positive. It can go up to 1, it can go up to, can go higher than 1. The farthest objects that we have been able to observe with current technology telescope is becoming Z of between 10 and 15, I think. It was around 10, but then this JWST, the James Webb Space Telescope, very much in the news. It seems to be detecting galaxies at Z higher than 10, 12. That is what I've heard. Some people are playing 15 or 16. That is controversial. Okay. Uh, you can also talk of the speed at which a galaxy is going away. Naturally, that is nothing but the rate of the change of the distance. It is the distance to the galaxy. It is receding. So the rate of change of distance is its recession velocity. And I can write it like this because you see there's a relation between d and the scale factor. So this is d over dt emission minus 1. So take the time derivative, put this d on this side. So d dot is a dot by dtm is a constant. By dtm is a constant. Uh, so d dot is nothing but So ATM is also a constant. So D dot is just A dot. So D dot is A dot, and then you can rewrite it in terms of D by dividing and multiplying that. D dot is A dot, and then you divide by A and multiply by A, you'll get D again. So this just is as follows from here. The recession speed is equal to A dot by A times D, and A dot by A is defined as the Hubble parameter. The value of Hubble parameter today is denoted by H naught. That's called the Hubble constant. And otherwise, in general, H is just A dot by. So the speed of recession is given by H times D. And if you look at today's universe, then this is speed of recession just H naught times D. And that is, or let me put it this way, that Z is also can be shown to be just V recession by C. C times the redshift, the recession speed, which today is just H naught times. And this is Hubble's law. The speed of recession for low redshift. This relation is only true for Z less than, much less than 1. And this is what Hubble discovered, that the redshift, he plotted redshifts of galaxies versus their distances. Distances you have to measure independently. For example, by looking at, you know, starlight. So if you are sure how much light the star, like a surface emits, how much brightness you are seeing, then from there you know the distance to the star. So this is Hubble's law, which follows from this definition of redshift and this definition of recession. And as you know, what value does Hubble constant take is a very hot topic always in cosmology. At Hubble's time, we found it to be 500 kilo in units of this kilometers per second per megaparsec. I forgot to mention the age of the universe since the beginning, since the Big Bang, is of the order of 1 over h. Now, this you can see here, no? Speed divided by distance is 1 over time, or distance divided by speed is time. So let's go back here. I should have told you one thing. When we solve these equations to find out the scale factor, it is easy to show that it goes to zero at a finite time in the past. So the universe is expanding, the scale factor is increasing, but it was zero at some finite time in the past. How long ago? Of the order of 1 over h. So you measure the Hubble constant. So how do you measure the Hubble constant? You can measure the redshift of a galaxy, you can measure the distance to it, and Hubble constant nothing but the slope of this line. Cz is proportional to d, and the slope of that line, which is the Hubble constant, the inverse of the Hubble constant, gives you the age about 10 billion light years, more precisely, I think 14 billion light years. And what's the value of the Hubble constant? Uh, Somewhere around 70 kilometers per second per megaparsec, but you may have heard of what is now being called the Hubble tension. You heard of the Hubble tension? There are one way to measure the Hubble parameter is just by distances of galaxies. Yeah, and that gives you some value. Okay, give some number. I think there are two numbers in the game, 72 and 67. I think the distances give you around 72. The other number comes from the model of cosmology, the so-called standard lambda CDM model, cosmological constant and dark matter model. When that is applied to the microwave background, that is the what you call a cosmological prediction of the Hubble constant. That is given around 67. Now I don't remember which one is 67, which one is 67. CFD is lower, is it? 67 and 72 is the distance. Distance, okay. Now these are different numbers. Where up to the error bars are now small enough that there is a contradiction. So that is what is being called the Hubble tension. This has become important in the last 4 or 5 years. It's a very serious situation because it either the because stellar distance measurement of 72 is wrong or the model of cosmology is wrong. Both cannot be correct. So if the stellar picture model distance measurements are correct, then there is a problem with the lambda CDM model. Our understanding of dark energy and cosmic acceleration might be wrong. So there's definitely a research problem to solve, which is attracting a lot of attention. What is the Hubble constant? That is a very open question. Okay, along with the Hubble parameter, we need to define one more thing. So this is the rate of expansion that comes from the Hubble parameter. The other thing is the rate of deceleration. And that is what is the rate at which the universe is slowing down? That is minus a double dot a by a dot squared. That's called the deceleration parameter. When this was first time, this universe was believed to be decelerating. So we talked of a deceleration parameter, not acceleration parameter. From this relation, you can show that dH by dt is given by this formula. It's very easy to rewrite this like this, okay? And but today we know that the universe is accelerating, which means the deceleration parameter is negative. Q is negative, so that the acceleration is positive, deceleration is negative. Because this is a double dot is negative, a double dot is positive, then Q is negative. If a double dot is negative, then Q is positive. Okay. And one other important thing, concept you should know is that what is known as a critical density, 3h naught squared by 8 pi g. What is that? Suppose lambda is 0 and the spatial section has 0 curvature, k is also 0. Then this is the Hubble constant today. H naught square equals 8 pi g rho by 3. The density of the universe for the case when k is 0 is called the critical density. Why? Because if rho is greater than the critical density, the universe is closed. It has to collapse with back on itself. That follows from looking at this equation. And if the density is less than the critical density, then clearly k is negative. The universe is negatively curved and will expand forever. So the critical density is just this ratio 3h naught squared by 8 pi g. It is the dividing line between closed and open universes. And we know we can measure h naught. So we know how much is rho c. This is, if I remember right, something around 10 to the minus 29 grams per cc. Your typical densities on the Earth are 1 gram per cc. And the universe is so rare, so sparsely populated that the average density is around 10 to the minus 29, 10 to the power minus 29 grams per cc. And perhaps the universe today, that's what observations suggest, is this marginal case, k is 0. Though it comes with its philosophical troubles, a k equals 0 universe is infinite. So why is the universe infinite? What is infinite? We have never seen anything infinite in our lives. Everything is finite. Infinite is a mathematical concept. What sense do I make of a universe which is endless? Philosophically troublesome. So at least I'm comfortable with the closed universe. It's like, okay, we talk about some other time. When the Big Bang takes place, it expands. It will reach a maximum size with contract. So somehow that seems less troublesome philosophically. And the universe has various kinds of components. It has baryons, ordinary matter, maybe it has dark matter, it has radiation. So the component under consideration, the ith component, it has certain mean density rho I. Divide that by the critical density. That is called the omega parameter for that particular component. So here we have to cosmologists talk of omega matter, omega lambda, omega dark matter. When we first hear it sounds very strange. This is what it means. Omega total seems, according to observation, to be 1. If you rho 1 plus rho 2 plus rho 3, all components put together, when you divide by rho c, you very good evidence that it is 1. Omega lambda, like you asked me yesterday, omega lambda is 0.7, 70% dark matter. Omega dark matter 0.24%, 0.25, and ordinary matter from which stars are made around zero point zero 0.04. So omega matter zero point zero 0.04, omega dark matter 0.26, omega dark energy zero point 0.7 roughly. So the universe has three main components. Assuming there is dark matter, or if not more, then it is dark matter. Omega dark matter, omega baryon that is called luminous matter, and omega lambda, omega dark energy. Radiation is very less. Universe today is not dominated by radiation. Which radiation we are talking about? The cosmic microwave background radiation with a temperature of 2.7 K, first discovered in 1965. We'll go through that history now in the next slide. And so, what do we think is the fate of what is the future going to be like? Going by today's observations, it seems so. This is the standard model. Omega matter is 0.3, 30%, including luminous. Omega lambda, the contribution to the density by the cosmological is something 0.7. Total is 1. That solution for the scale factor or distances between galaxies proportional to the scale factor in the future and in the past. So now is here. So these curves tell you how the scale factor is changing with time. Every one of them goes to a singularity. That's the Big Bang. The universe started, according to this model, the universe started with the Big Bang. But of course, this is classical GR. It is likely to be breaking down because the densities become very high. The density goes to infinity. Quantum gravity will take over. So, how will quantum gravity modify the Big Bang? Was there a beginning, or is it eternal? Like, cyclic universes keep doing this all the time. Why are they doing this? Nobody knows. So, this point is unclear. Was there a beginning, or is the universe eternal? Are there multiverses? Don't know. But at least around this we can make observations. And this is the current favored model. And if omega matter is greater than 1, that's a closed universe. So that way, it began from singularity, is fall back, closed universe. And again, this is the so-called big crunch. Big bang, big crunch. Then the other models, omega matter is 0, omega matter is zero point 0.3, omega matter is 1. This is what current observations seem to favor. Okay? So please, any questions? Okay, so in the last slide, okay. I think we have discussed enough about dark matter. I don't want to go through dark matter and once again, unless you have questions. Okay. Okay, so this will be the last slide. So instead of doing this with equations, it will take a lot of time. I want to, if you know this, then it's a little boring. If you, so I want to tell you for those of you who are not familiar, what was the history of the universe since the Big Bang up till now? We can also look at it from the point of view of what happened since general relativity was discovered. So 1929, Hubble discovered the expansion of the universe. Uh, then comes the debate. It's expanding, all right, but is it eternally the same or is it evolving? Was there a beginning or was it there forever? So there were two schools of thought, the steady state school. The steady state universe obeys the perfect cosmological principle. It has no beginning. Yeah? This is I think the names Bondi, Herman Bondi, Gold and Oil. Bondi, Gold and Fred Oil. Fred Oil, you know, Professor Mathematics, PhD supervisor. So Zanander also was seriously involved with the steady state theory. So steady state theory versus the Big Bang theory. Interestingly, I think the name Big Bang is also due to Fred Hoyle. You know, no? I mean, he said it out of some kind of in a derogatory way. Big Bang. The name stuck. The name Big Bang cosmology is also due to Fred Hoyle. But Fred Hoyle was a supporter of steady state cosmology. So there was this debate through the 40s, through the 50s, with no progress in sight, with people looking for evidence of evolution. You're looking at galaxies. Are the galaxies in the past different from the galaxies now? Then, comes this. Was this the situation in around the early 60s? You probably know the name of Jim Peebles. He won the Nobel Prize for Cosmology a few years back, 4 5 years ago. Jim Peebles was then a student in Princeton along with Robert Dicke. And Dicke had this idea that, of course, it was first done by George Gamow and then also repeated by Peebles and Dicke, that if the universe had a hot beginning, while it was cooling, it may have made some of the elements, then some of the nuclei may have been made in the early universe. Please go and do those calculations. So, Gamow in the 1940s, I think, and then later other people, including people, did these calculations, which I'll come to in a moment, that some of the elements, lighter elements like helium and also I think lithium and deuterium would have been made in the very early universe just after the Big Bang. And more importantly, uh, the very hot radiation from the early universe would have cooled with the expansion. Temperature of the radiation falls inversely with the scale factor. So there would have been cooling. And given some estimate that we have of the age of the universe, because we know the Hubble constant, by now it ought to have cooled to something around 10 degrees Celsius. That's the estimate that Dicke and people came up with. This is early 65. How many of you know this story of the discovery of the microwave background? Yeah? Okay. But is it worth telling again? Okay, so yeah, everybody knows, is it? you know. Yeah. So still for fun, I will repeat it. The interesting part is that Dickey said, let's make a microwave antenna with which we can look for these 10-degree radiation. We actually started making the telescope at Princeton, and not far from them, there is this Bell Labs. Not very far from them, there are these two radio engineers who have known nothing about astrophysics and cosmology, who are preparing a making a radio antenna to detect background terrestrial noise so that telephone communication can improve. So I'll keep this short because it's a story. And they are detecting a uniform phase coming from all sides, which is not going away. And full 1 year is gone trying to understand what is this irritating noise coming from. And then they somehow it becomes clear that it is not terrestrial. It seemed to be coming from outer space. So they contacted BT that this problem is there. Can you help us? So then he told people that they have found what we were looking for. It had all the right characteristics. So this the microwave diagram was discovered in a very dramatic and unforeseen way. But in any case, I think if not Penzias and Wilson, Dickey would have. They were doing the right thing. They were making precisely the same kind of antenna that Penzias and Wilson used. But as a result, Penzias and Wilson got the Nobel Prize, which he did not. This is life. Penzias and Wilson didn't know what he did, but they got the Nobel Prize. So that's how life is. And that, as you know, put an end to the steady state versus the Big Bang debate because there's no way to explain such a uniform microwave background radiation of such a low temperature. You can't explain it from starlight. That is the consensus. So it must be a leftover from the early hot beginning of the universe. And so this is the next major milestone after the discovery of the expansion of the universe, discovery of the cosmic microwave background. In between, also discovery of radio galaxies, which are seen to evolve. But another factor in support of Big Bang cosmology, this radio galaxies evolve with time. Then came the epoch from 1965 onwards of studying the microwave background more and more carefully to get the spectrum at all wavelengths. Plus, another new problem emerged, namely, this radiation cannot be perfectly isotope. Why? Because in the very beginning, the very early universe, all the matter would have been ionized. The radiation was so hot that hydrogen could not have been neutral. It would ionize the 13.6 eV line would be gone. Hydrogen and everything would be ionized. At which stage matter and radiation would have been in thermal equilibrium with each other. And there would have to be some inhomogeneities in the matter distribution right from the Big Bang so that galaxies can form. Yeah. If matter distribution is exactly uniform, how will galaxies form? Galaxies are density inhomogeneous. To form them, you need to have some seed inhomogeneities to form galaxies with likeness. If you see a grown-up person, you're sure this person was once a baby who was born. And if there are no babies, there will be no person. Same way, if there is no initial seed, there would be no galaxies. Then the matter is completely uniform. So if there is an inhomogeneity in the matter distribution, there has to be an anisotropy in the temperature to the microwave background. Where there is more matter, the radiation would actually be cooler because matters tend to keep. Where there's less matter, the radiation will be hotter. Okay, so it was known that there have to be temperature anisotropies in the radiation of the order of delta T by T is 10 to the minus 3. Okay, delta T by T should be of the order of 10 to the minus 3 in radiation. That's the anisotropy in the temperature. If you look at one direction and you look at the neighboring direction, some angle away, say about a degree away, the temperature variation should be delta T by T of the order 1 over 1000. The temperature inhomogeneity if we want to form structures. In order to form structures, you need some inhomogeneity in matter. If that inhomogeneity is too low, you won't form structures. To form structures, you need some delta rho by rho, it's called density inhomogeneity, delta rho by rho early on, which will be of the order 10 to the minus 3. So delta T by T is of the order 10 to the minus 3. And people were looking for it and not finding it. So in 1991, you know Kobe satellite, cosmic background explorer. In 1991, great year, Kobe found temperature anisotropy delta T by T 10 to the minus 5. That in a way is a disaster. It's good. Thank God it is there. If it was not there, Big Bang cosmology would be out. Can't can't form galaxies. They found delta T by T 10 to the minus 5. Then how do you form structures? That is where dark matter comes in, not 1991. Dark matter is already introduced by Jim Peebles around 1983, I think, to precisely with this idea, how to form galaxies and yet not have delta T by T 10 to the minus 3. You're following this? Temperature anisotropy at 10 to the minus 3 level was not found. How do you form galaxies? You say that the universe is dominated by dark matter. Dark matter doesn't couple to radiation. It can have a delta rho by rho, which is 10 to the minus 3. That will not produce a delta T by T, which is 10 to the minus 3. Delta T by T is produced by ordinary matter, luminous matter. So delta rho by rho dark matter was 10 to the minus 3. Delta rho by rho luminous matter 10 to the minus 5. Delta T by T radiation 10 to the minus 5. So that is how dark matter became so popular because it permitted galaxies to form in spite of the temperature anisotropy being as low as the detected 10 to the minus 5. And since then, the dark matter story has stayed. Dark matter is very important for cosmology and structure formation. And then they say it is also able to explain rotation curves of galaxies, which is where I think there is a problem. You are good there, you are not good here. Please don't oversell. That's the rejoinder that we have a problem. We have dark matter success in structure formation. We don't have dark matter success in galaxy rotation curve. We have Mond success in galaxy rotation curve. We have Mond failure in structure formation. We are physicists. Please solve the problem. Yeah. Okay, so that is the history of cosmology. 1991, CMB anisotropies were discovered. Then that curve has been improved. WMAP, Planck, successive CMB satellites. That is the story stands, I think. I don't think after CMB and isotropy discovery, anything great of that order of importance has happened in cosmology. So the epoch-making discoveries are in cosmology are first to show that there are galaxies outside our galaxy. Milky Way is not the whole. The universe is expanding. Hubble 1929. Cosmic microwave background discovered 1965. And isotropies in the microwave background discovered 1991. And yes, of course, acceleration of the universe discovered 1999. And that is where the picture stands today. The standard lambda CDM model, this one, no, yes, omega matter zero point 0.3, omega lambda zero point 0.7 is the standard model of cosmology. I think it is beginning to break down. It has trouble with Hubble tension, and also dark matter is not being found. Hundreds of experiments have been done to look for dark matter. But the problem is that we don't even know what we are looking for. There is no standard model of particle that is candidate for dark matter. If I knew that I look for massive neutrinos, it is easier. I don't know what I'm looking for. I don't know whether it is there. So you're looking for a needle in a haystack. So you don't know what the needle looks like, and you don't even know whether the needle is there. Because it has no electromagnetic interaction, it has no strong interaction, it has no weak interaction, it has only a gravitational interaction. So if you put a detector here, it has no gravitational interaction with the data because it's very weak, just one small detector. Okay, right. So this is the thermal history of the universe. If you have read this book, First 3 Minutes by Steven Weinberg, very beautiful book, popular book, he gives you this picture that we understand the universe from about 1/100th of a second since the Big Bang, when the microwave background was extremely hot, 10 to the 9 degrees Kelvin. As the universe was cooling, it is made up of elementary particles, quarks, electrons, neutrinos. Quarks will form protons and neutrons, and protons and neutrons will combine to form nuclei like helium or the little traces of deuterium. Mainly helium, you know this issue that there is far too little helium in the stars, not enough time for stars since the Big Bang to make helium. The universe is about 25% or little bit here and there, that number. Most of it, as you know, is hydrogen, and around 70% is hydrogen amongst the luminous matter. Around 25% is helium, and the rest, everything, iron, carbon, oxygen, is around 4 or 5%. Stars can only make about 2% helium, and so this is a great triumph of Big Bang cosmology, the work of Jim Peebles and I think Gamo also had this number and a few others to show that most of the helium was made just after the Big Bang. These are great calculations. Human beings to sit on Earth and show that there was an early hot beginning, which where the helium, most of the helium was made. This is I think, a great success of Big Bang cosmology. Then, for most of its history, early history, up to about 180,000 years, roughly around then, the universe continues to be radiation dominated. Nothing happens. It expands, it is dominated by radiation. And once as it is expanding, it is cooling. And when it becomes cool enough, there comes a stage when it can no longer ionize matter. It cannot ionize hydrogen. So neutral hydrogen forms, atoms of hydrogen and other heavier elements, atoms start to form. Once atoms form, this will decouple from radiation, right? The radiation cannot ionize it, decoupling, from the decoupling of phase. At the time of decoupling, whatever density anomalies were there in matter will be imprinted as temperature anisotropies on the microwave background radiation. And this delta T by T is what we see in today's. This is what Kobe and Planck and WMAP detected. Delta T by T of the order 10 to the minus 5. After that, the universe becomes matter dominated. This is happening if you talk of age in terms of redshift. The coupling is around Z of 1000 or 1100. Matter domination begins around Z of 1000. Then galaxy formation happens when delta rho by rho becomes order unit. Density inhomogeneities earlier on decoupling around 10 to the minus 3, and in about a thread going from 1000 to 1, around redshift of 10 or thereabouts, galaxy formation begins. And of course, our location, our epoch in history, Z equals 0. That is now somewhere between Z equals 10 and today galaxies form. There are, for some reason, black holes at the center of every galaxy. So this is a good, very good understanding. Apart from, of course, the very early universe, we don't have a quantum theory of gravity. We don't understand the Big Bang. Then this question which we touched upon yesterday: why our universe is mostly made of matter and has almost no antimatter? What is the dark matter issue? Is it there? Is not? Is there? What is it made up of? What is dark energy? Why is the cosmology constant if it is non-zero? Why is it non-zero yet so small? So I hope you get some flavors of cosmology from this lecture. There are important ones of dark matter, dark energy, matter, antimatter symmetry, Hubble tension. So I think the picture will change a great deal in the coming decades. There will be the lambda CDM. I think there's no lambda, there will be no CDM. I think there will be a difference here. Okay, good. One time. So thanks for attending my 4 lectures. So nice to get to know you. And tomorrow I will officially see you. But you are welcome to send me an email if you want to ask something. You have class in the morning also. Tomorrow also. All right. So we can close. There's a talk here at 4 o'clock. We still have 2 minutes, but we can discuss that.
How is the age of the universe
Yeah, so for that we must believe in a model. Without a model, you cannot predict. Of course, stellar ages can be told. That suppose it began with hydrogen, we know what is the rate at which it makes helium. So we can, looking at the helium abundance or abundance of other elements, we can guess the age of stars. Or in the age of Earth comes some radioactive uh, decays. So the Earth's age is well estimated to be about 4 to 5 billion years of that order. Same for the sun. Stars, the oldest star, the globular cluster, will be about 10 billion. Universe age can only count from a model, and it is of the order of 1 over the Hubble constant. So that physics you understand. V equals h naught b. Divide b by v, distance over velocity. That will give you the time. That is 1 over h. D can be measured from astronomy. Speed of precession can be measured by measuring the redshift. It is this relation. Speed is z, cz. So the h is of the order of 1 over h naught, and more precise just by solving this equation. So what I want to say. Right. These plots are solutions of the Friedman equation. So, depending on what you gave for X naught today and the deceleration parameter, you can find out this point. So, the aid, to answer your question more precisely, is determined by solving Einstein equations after measuring the Hubble constant and the deceleration. It is this from now. I'll find out when it reaches it. But it is definitely modeled then.
Can't really be sure of it.
Yeah, see, for example, maybe it is eternal, you see. What is age since the Big Bang? But what if there was something before the Big Bang? Then age takes a different meaning. Maybe you are asking since the Big Bang.
Right. I meant, like, for example, in the omega n equals 6 model, it predicts around 5. A little
Yes, yes. So omega m is something you have to keep knowing from measurement. What is omega m? The density of ordinary or dark matter, density of dark matter. This number has to come from us. So it's dependent on observations and on the model. This number changes. But at least we are thankful it is more than the age of stars. Coming 14 billion years, probably it was around 10 billion years. There is consistency. If stars came older than the Big Bang, you can throw out the Big Bang more. So we are happy there is still a time. But of course, worrisome things are happening. JWST is finding older and older galaxies. If you found a galaxy older than the Big Bang, there'll be trouble. So it's a very interesting situation. I don't take any of this as the final word, although it's presented with great conviction. The conviction lasts for 10 years, 20 years. So, yeah, you were saying?
My question is about the omega n. Omega n is equal to 6.
No, that's a toy mod.
When it will peak.
Solve the equation. Yes, yes. When you can solve this equation, I don't have an answer offhand. You solve this, k is only plus 1, and I know to put omega n is 6. So rho is 6 times rho c. Rho c I know. So I put today's value, and then it has certain dependence on the scale factor. We'll have to solve this equation. The solution of the equation will be this curve. And then we can run from the solution, we can read out the maximum.
So if it is a closed universe, after a big crunch, then there will be again a big bang.
No, here the GR is breaking down, you see. We don't know what's happening here. We don't know. This is gray areas. See? Quantum gravity. You need quantum gravity. You need unification of forces. So maybe it is not like this at all.
Below a certain average distance between galaxies is uncertain.
Inhomogeneous.
No, I mean, like you said that it's a gray area whenever.
Using scale factor. When I say gray area, I mean time-wise. Very close to the Big Bang, t equals 0. General relativity is breakdown. It also has to be unified with other forces. Our picture of space-time itself is suspected. So we talk about it for 2 minutes. We take space-time for granted. What is space? The distance between bodies. What is time? The interval between events. This interval is the interval between events. But look at quantum theory. Where you cannot talk of distance between bodies. The electron, take the electron, take another electron. This is wave particle duality. In a sense, it is everywhere, not just here, it's everywhere. The wave, when it leaves the detector, it's everywhere. This electron is also everywhere. What is the distance? Space is not well defined quantity theories, except when the universe is dominated by classical thought. When I write down the Schrodinger equations for quantum mechanics, I take space and time as given. But who gave me that space and time? These classical bodies. But these classical bodies are a limiting case of quantum theory. So the theory is depending on its own limit. Imagine that suddenly all the classical bodies become disintegrate and become electrons, and suddenly everything is quantum. What do you lose? You lose space and time. But the universe is still there. No? So I have to learn how to describe quantum theory without space and time, and that is essential for understanding what happened at the Big Bang. So this idea that there is a singularity pre-assumes that there is a space-time lasting until then. So what new research suggests that both space-time and matter are emergent ideas. And what do they emerge from? Mathematics. When you go to the very fundamental level, all you are left with equations. Suppose you write the Dirac equation for the electron, there's a wave function, there's spatial. For me, at that fundamental level, there is no distinction between physics and mathematics. The physical universe is not different from the mathematics. That is my. Here it looks very different. What is the number one is very different from one. But go to basics. Electrons, quarks. What is an electron? It's not a particle. It is not a wave. The electron is a solution of a mathematical equation, the Dirac equation. So whatever I'm left with, I'm just left with an equation with certain mathematical concepts, which eventually can be reduced to numbers, real numbers, complex numbers, quaternion, octonion. The numbers. My equations are coming from numbers, and numbers equations are what are particles are equations. That's if I can't do it in any other way, then I have to say it is the equation which is the particle. I mean, the concept is this. I'm not saying that this written thing is the particle, but the concept of a particle and of space is indistinguishable from mathematics which describes it, and mathematics is reducible to numbers. The universe is just ultimately it is just that. Comes back to the same question as yesterday, then why is it there? That I don't know. So hard question. You can reduce it to mathematics and happily, and then you see if there is no space and it is just mathematics. I don't know if there is any place for God. But that is, we won't go there. Maybe God is mathematics. But at least mathematics is sacred. You cannot do, you can do away with the physical world, you cannot do away with mathematics. So we are also mathematics. But why the maths is there, I don't know. Anything more? Did you have more cosmology lectures this week? Some more? No, Singh will teach structure formation. Alright, so let's stop. I think we are waiting. Yes. I support that. This cyclic cosmology, I don't follow too well. This is because he said there is observational evidence for it in the microwave background. That I don't know, but I strongly agree with him that there is something before the Big Bang. So I would support this picture that there are Big Bangs happening all over all the time. And it's like you could try to picture the universe as a box of gas, except that this is a mathematical gas, it is not particle. And the gas suddenly, suppose most of the gas goes to one corner of the box. It's a fluctuation. Fluctuations happen. Very unlikely, very rare, but they happen. It goes to one corner of the box, then has to come back. That coming back is like the Big Bang. So in this great box of gas, there are these fluctuations happening randomly, and they are followed by big bangs. So in that sense, I support the idea that this is happening all the time. So comes back, and this box is mathematical. When the explosion happens, space, time, and matter gets created, and then everything will fall in structure. It will again become black hole. It will again become Hawking radiation. That will become a part of the gas once again. Again, there will be some other fluctuations. So someday physics should try to find out why it's all this. That is very strange. I don't know. Maybe our brains are not adapted to answer that question. We keep thinking the brain can answer everything. I mean, maybe it cannot answer. It can answer how, but it cannot answer why. Because coming to think of it, what is the brain? Brain is also elementary part. The elementary particles are trying to understand elementary particles. So they can understand, but elementary particles are asking other elementary particles, why are we there? Nobody will know. This is one thing probably on the part. Yeah, yes, yes.
So from the two fragment equations.
Sorry?
The two fragment equations.
Yeah, yeah.
So we can also like derive the third one, that which has a we can also derive the third equation.
Continuity.
Yeah,
continuity.
And
yes.
we have density as a function of scalability.
Yes, yes.
So for radiation, the W is 1 by 3. So from that we get 8 power minus 4. For matter, we know it's 8 power minus 3. That's x, y, z. But for 8 power minus 4, that what's the extra 1 by 8?
Why is it? Because there is pressure, you see. Pressure is proportional to density. P is 1/3 rho. That's mathematically or physically? So mathematically, it would be like which equation should I look at? Yeah, the continuity equation gives you rho as 1 over A4 because there is pressure. The continuity equation involves pressure also. So when you put 1 over A4, the solution will change. And physically, see what is matter doing is losing energy. Energy density is falling because it is doing work. It's doing work against expansion. When we stretch the volume, it is doing work, so density will fall. When there is pressure, there is extra work.
We are taking the redshift.
Sorry?
We are taking the redshift into account.
Yes, yes. When there is pressure, there is extra work to be done, so the density will fall faster because of the pressure.
Just another, when we are saying it's homogeneous and isotropic, so before like it's in Einstein field equation, we take for the 0, 0 term and trace for these two Friedman equations. So before that, we also need to make one assumption like what will be our reference frame? Is it rest frame or like?
Yeah. So that is here. There has to be assumed definitely absolute frame in which the microwave diagram is isotropic. That assumption has to be there. If you move with respect to that frame, you will see an isotope. So there is an assumption of a special frame. You are right, that's usually not emphasized. The Earth is moving through that frame. That is why we see a dipole in the dipole anisotropy of the microwave diagram. The preferred frame is one in which the microwave background appears isotropic. You are right.
So we are ignoring translation.
In this, the dipole anisotropy of the microwave background is neglected. So those are like what is called there's a name for the peculiar velocities. So the expansion is, let's say, radial, but locally there are perturbations, no? The sun is going around the galaxy, or our galaxy is pulled towards them. Those are called peculiar velocities. V total equals V Hubble plus V peculiar. You understand? So in this simple treatment, we ignore. That's not a part of cosmology. That's a local perturbation.